Hello everyone and welcome back to General Chemistry Laboratory. This week in Chem 1240 we're working on calorimetry, which comes from the word calorie, which used to be main unit for measuring energy. Although now we measure energy primarily in joules or kilojoules in the International System of Units, the name calorimetry still refers to a variety of techniques used to determine energy input or output of a chemical reaction. In this lab today, we're looking at only parts B and C of the procedure for calorimetry. In part B, we're looking at the neutralization reaction, the reaction between an acid and a base. And in part C, we're looking at the reaction of dissolution of a solid ionic substance like a salt in water. So first, let's discuss part B. As I mentioned, it's a neutralization reaction that we're interested in. Reaction between a strong acid, which contains a hydronium ion, H3O+, and the strong base containing hydroxide ion, OH-. This here is a net ionic equation of the reaction that's going to occur. Hydronium ion and hydroxide are going to react, producing two water molecules. This coefficient 2 is going to be important for our calculations. We'll look at the data sheet. We're going to specifically talk about this too, so keep that in mind. This reaction, neutralization reaction, is expected to produce heat, which means it's going to be an exothermic process. Here we'd like to differentiate between heat of reaction and enthalpy of reaction. The absolute value for enthalpy of reaction is equal to that of enthalpy of reaction, but the difference is in the sign. For heat of reaction, we're looking at what happens to the surroundings of the environment. And imagine if you conduct a reaction in a certain container and the reaction produces heat, the heat is going to escape the container and is going to go to the surroundings. So surroundings or environment are going to gain heat, and therefore for exothermic process, heat of reaction, typically designated as Q, would be positive. Here we're dealing with Q, and N stands for neutralization. In contrast to heat of reaction, enthalpy of reaction, or delta H of neutralization in this case, is going to be negative because enthalpy looks at change of energy with respect to the reaction itself. So reaction mixture is going to lose energy because it's going to be transferred from the reaction mixture to the surroundings. And therefore reaction mixture itself loses energy. Therefore enthalpy of neutralization is going to be negative. Again, same absolute value, different sign. Heat of reaction can be found as specific heat capacity of water, because water is the main product, times mass of acid in the base in the calorimeter, times change in temperature. So specific heat of water is a very important parameter for any substance. It shows how much heat it would take to raise temperature of 1 gram of water by 1 degree. And it's a constant that's provided in your lab manual. We can easily determine mass of acid in the base because we're going to measure their volumes, and density is assumed to be 1 gram per milliliter for both. So the only question then remains, how we're going to find delta T. So delta T is found by using temperature probe attached to a data logger, which you will see in the experimental portion of this procedure. So delta T is determined experimental, and then heat of reaction is calculated, and then enthalpy of reaction can be also found by simply changing the sign in front of the heat. So once again, specific heat capacity of water is given at 4.18 joules per gram per degree. So in other words, it takes 4.18 joules of energy to heat 1 gram of water by 1 degree. Delta T is found as final temperature of the reaction mixture minus initial temperature. And because we're talking about exothermic process, temperature is expected to rise as heat is being produced. So final temperature is going to be greater than the initial temperature, and delta T therefore is going to be greater than 0. So in this experiment we're expecting delta T to be greater than 0. Specifically for this experiment we're using two solutions. We're going to be measuring exactly 50 milliliters of 1.1 molar hydrochloric acid into one graduated cylinder, and exactly 50 milliliters of 1 molar sodium hydroxide in another. Just to review, HCl is a strong acid, generates a lot of hydronium ions in solution. Sodium hydroxide, being a strong base, generates hydroxide ion. So let's think about this. We're using same exact volumes of two solutions, but molarities, albeit close, are not the same. This one is 1 molar, this one is 1.1 molar. So the question is which is going to be a limiting reactant. Think about this. Moles of reactant are found as volume times molarity. Volumes are the same, so molarity is going to be the determining factor. The one that is going to have lesser molarity, in this case sodium hydroxide, is going to be the one giving us fewer moles, and therefore it's going to be limiting reactant. So limiting reactant here is NaOH or OH minus, just the ion. Because we're using net ionic equation, hydroxide ion here is expected to be limiting reactant. So you're going to find moles of NaOH by taking molarity of NaOH times its volume. Don't forget to convert volume to liters. And then you're going to assume hydroxide is your limiting reactant because its molar concentration is less. And then you're going to have to find how many moles of water are going to be produced. Remember, 1 mole of hydroxide is expected to make twice as many moles of water. So to find moles of H2O, you're going to take moles of hydroxide and you're going to double it. It's very, very important for your report sheet. So next I'm going to show you a hypothetical curve that's expected to be obtained, and this is what you're going to see on the screen when I run a trial for you. I can't guarantee you that I will be able to to send you a curve like this, but I am probably going to get you the value for delta T, so you can then calculate your own heat and enthalpy of reaction. Or another way I think I'm going to do it is I'm going to give you a link to a simulator, and you can pick your own concentration of both HCl and NaOH close to what the procedure would suggest, and then the simulator will give you the change in temperature. But here what we're doing is we're going to place our base sodium hydroxide in the coffee cup, in the styrofoam cup, which is used as a calorimeter here, and then we're going to put a temperature probe in, and then we're going to start collecting data. And at first we only have an NaOH in the cup, so temperature is not changing because it's only one solution, nothing's happening to it. Once we record this constant temperature for about 100 seconds or so, I'm going to lift the lid of the calorimeter cup, and I'm going to slowly add and carefully add hydrochloric acid, source of hydronium ion. As you can see, as soon as acid is added, temperature starts rising fairly quickly and abruptly. It rises until all of the sodium hydroxide is used up. Remember, NaOH is our limiting reactant. Once that happens, temperature sort of levels off. You'll notice that up there can't quite reach, but that portion of the curve, you notice it has a little bit of a negative slope. It's decreasing a little bit. That's because at that point the temperature of the mixture in the cup has significantly risen to about 30 degrees or so, and so the solution inside the cup is warmer than the surroundings, so heat starts flowing from the mixture in the cup to the surroundings, cooling it, and that's why you're seeing the decrease. So very importantly, on a curve like this, it's important for you to know how delta T can be found. Well, initial temperature of sodium hydroxide is clearly right here. This is the portion of the curve we originally recorded before we add the second reagent. For the second one though, how do we find final temperature? So what we do is we draw the tangent line to that portion of the curve, and then we also draw this vertical line through the time when we mix the solutions. So this is called mixing timeline, going vertically, and then the tangent line for the final portion of the curve is drawn until it crosses with mixing timeline, and then you're supposed to go straight over to y-axis to find your final temperature. So in my case, final temperature is roughly 31.1 degrees. This diagram here is very similar to what you have in your lab manual in description of the procedure for this experiment. So once again, increase in temperature is expected when acid and the base are mixed, and final temperature is found from the curve like this. So if you were to do this experiment in class, you would be able to follow these temperature changes on the screen of the data logger, and then you would print a curve like this, and you would find your own delta T. Next, we're going to look at part C. Part C is dealing with enthalpy of dissolution of salts. So here in the coffee cup, we're going to have certain amount of deionized water, and then after collecting temperature of just pure water in the cup for about 100 seconds, we're going to add somewhere between 2 and 3 grams of a solid ionic substance like a salt to the water, and we're going to swirl the solution until the solid salt completely dissolves, and we're going to measure corresponding temperature change, which will then allow us to find enthalpy of solution. So here we're looking for enthalpy of solution. S here stands for solution. We have two bodies, if you will, two substances here, and we have to evaluate enthalpy changes for both. Enthalpy of solution is found as enthalpy change of water plus enthalpy change of the salt itself. Just like before, enthalpy of solution is numerically the same as heat of solution. The difference is in the sign. So enthalpy of solution and heat of solution are the same as far as absolute value is concerned, but have a different sign. As an example of salt, here in my notes I'm using potassium chloride. So potassium chloride is going to dissolve in water, and it's going to also dissociate. And this is where a chemical part of this comes in. Technically, when the substance dissolves in water, it's more of a physical process. But in this instance, there's a chemical interaction between water molecules and ions of potassium and chloride, where water surrounds or hydrates each of the ions, and that's where a chemical portion of this comes in. So dissolution of the salt is accompanied by its dissociation, which is a chemical change. So there are two enthalpies that are calculated here. First one is enthalpy change of water. Enthalpy change of water is found as minus heat change of water, which is found as specific heat of water times mass of water in the cup times change in temperature of water. And then you also have to find enthalpy of salt, and enthalpy change of salt is found as negative heat change of salt, which is found as specific heat of salt times mass of salt times delta T of salt. So here you find two enthalpies, and then you add them up together to find total enthalpy of solution. There are two different substances involved, so we need to know two different specific heats, and I will be providing those in the announcement that I'll put on Canvas. So enthalpy of salt is something that you will need to have depending on which salt you are assigned. And then mass of salt will be provided to you as well as mass of water. What about delta T? Well, delta T, in this case, because water and salt both start out at room temperature and end up in the same solution, we're assuming that temperature change for water is going to be the same as temperature change for salt, which we will have to find experimentally. So the salts that I picked for this experiment at least if you were to do it in class, all salts used in the actual lab have such a situation where heat of solution is negative, meaning environment donates or provides heat or loses heat to the reaction, and the reaction mixture itself absorbs heat, which means then delta H, or enthalpy change of solution, is expected to be positive. So when enthalpy change of a reaction is positive, it means that reaction needs to obtain or absorb heat from the surroundings, from the environment. This type of reaction, of course, is referred to as endothermic. So we're expecting salts to dissolve endothermically, although it's not necessarily always the case. And there are salts that may dissolve exo- or endothermically. It's just I picked for this particular experiment salts that would would dissolve, endothermically. When you use a simulator, you will see there are only 2 salts on the list that is provided in a simulator. There's lithium chloride and ammonium nitrate. And you can play around with this, and you can see which salt dissolves endothermically and which dissolves exothermically. So with salts, when they dissolve in water, it can be either endothermic or exothermic process. It's just I picked endothermic because often students have a misconception that whenever you dissolve something in water, heat must be produced, and it's not necessarily the case, which is what I wanted to illustrate here. So what would the curve look like, and how would we find delta T? Let's take a look. So this is the example that I picked. This is potassium chloride. So I actually took a little bit more salt than probably you would be recommended to take. I took 4.3 grams of potassium chloride, and I added 20 milliliters of water to my calorimetry cup. I started with only water in a cup. I immersed the temperature probe, started reading temperatures. You can see temperature as we expected stays constant at first because there's only water present in the cup at this point. And then once about 100 seconds have passed, so you can see about 100 seconds have passed. I lifted the lid and I added my solid salt. At this point you have to either stir, which is not ideal, because if you stir, it means that stir will be heating your temperature probe, and that creates all kinds of noise, if you will, or you can just swirl the cup gently, allowing the salt to dissolve completely. And what you're noticing, of course, is temperature is dropping. So this is in fact an endothermic process where heat is being absorbed from the surroundings by the reaction mixture. So once the salt has dissolved completely, reaction pretty much stops, and temperature starts leveling off, although you do see a little bit of a positive slope right here at the final portion of the curve. That's because at this point the temperature of the mixture is significantly lower than that of the surroundings, and so surroundings start bringing heat to the reaction mixture, warming it back up. So how do we find final temperature at this point? Well, initial temperature is, I hope, self-explanatory. What about final temperature? Once again, we draw the mixing timeline right here through the point in time when the salt was added to the water in the cup, and then we draw this tangent line through this portion of the curve until it crosses with the mixing timeline, and then we go over horizontally to find our final temperature. So in my case, final temperature was something like 12.8 degrees or so. So it went down all the way from almost 24 degrees all the way down to about 13 or 12.8, so quite a big drop. So here, as we expected, delta T is going to be negative because final temperature is less than initial, and so delta T is going to be negative. Meaning that heat of solution is going to be negative, but enthalpy of solution must be positive. So now let's go ahead and take a look at your report sheet that you're going to fill out. Again, we're only looking at part B and C. We're skipping A, so you're responsible for pages 158 and 159. On page 158, for enthalpy of neutralization, we're only looking at HCl and NaOH. However, when you're using a simulator, you may want to also run a reaction with similar concentration of nitric acid instead of HCl. What you're going to see is temperature change is going to be very, very similar, if not exactly the same. This is because both HCl and HNO3 are strong acids, and they both generate hydronium ions, so your net ionic equation is not affected. But you're only going to do HCl and NaOH calculations for 2 trials. And you're going to be given experimental parameters, and you're going to have to do calculations for enthalpy of neutralization. I'd like to point out that here they have under number 6 it says heat evolved, and then under number 9 it says delta H. So for heat, make sure you have in this instance positive value, and then when it comes to delta H, switch to negative value. For moles of NaOH, you'll find it through molarity and volume given to you, and then to find moles of water, don't forget to double your moles of NaOH to find moles of water, as we discussed, and you have to show calculations here on the bottom of the page as well. And then for part C, for page 159, you will be given a salt, you will be given its specific heat, you will be given its mass and mass of water in a cup, and you're going to have to find heat change of water, heat change of salt, and then add them up to find total. Now again, they are not doing this for calculation portion very clearly because they have heat for number 2 and heat change for number 3, and then numbers 4 and 5 is enthalpy. So in this case, heat change has to be negative, and then enthalpy for number 4, 5, and 6 must be negative. Again, you're going to do 2 trials, and you're going to have to show calculations on the bottom of the page. In the next video, I'm going to demonstrate the procedure for this portion.